Okay, why don't we get started? A little bit of administrative work here. You'll notice that there's a couple things going on. First of all, I want to make sure you realize that there are 3 classes this week. Don't forget. Second, we've agreed this is the midterm day. Fine. Third, if you've seen the announcements, I posted the solutions to Homeset 1 on Gradebook, and I gave the assignment number 2, which is due this Friday. The problems in this next set are, some of them are rather easy, some of them make you think a little bit more, not just routinely work through some things. So it's worthwhile looking at that. Okay, what I want to start out with now is to review very quickly what we did last time about the queuing comments. First of all, we have this simple model of a queue. Typically, it's a single server queue. We have this rather sophisticated notation where this describes the arrival process, this describes the service process, this tells you how many servers there are, this tells you how much storage there is, and this talks about a population being finite. Mostly, we just use these 3. If the others are missing, you assume they're both infinite. And our notation we'll review in just a minute again. The inter-arrival time density is given by A of t. The service time density is given by B of x. And we drew this particular interesting diagram here, which we'll use over and over again to describe what's happening in time at the queue and then what's happening at the server. And we see, for example, customers coming in, they hang around a while, they go into the queue, then they go into the server, and then they leave. So this is their total time in system, this is their time in service, this is their waiting time. We know the distribution for this service time, and we know the distribution for the inter-arrival times. What we typically look for is the time in queue and the time in system, very much related as you might expect. And I just reminding you here, the notation we're using for these variables for the inter-arrival time, remember A of t is its density, service time, B of x is its density, the waiting time we're going to use W to describe. So for example, this is the density of waiting time. And system time, total time in system, Q plus service, has the little letter S describing its density. And we introduced 2 other variables here. One of them was N of t is the number of customers in the system at time t. And by system, I mean the entire queuing systems, Q plus server. And U of t, which we're going to get to in a moment, is the unfinished work in the system at time t. If you look at the system at time t and let no other people to come in, how long will it take before the system empties? And the unfinished work is descriptive of what I mean. How much work is there that's not yet been done at that time? Okay. Now, I want to introduce a new diagram. It's all about U of t. So let's create an axis here. That's the time axis. And what I'm plotting here is the unfinished work. I'm going to show it to you now. We won't use it for a while, but it'll help give you some ideas to what's going on. In fact, let me put this on a separate page. It's a little bit easier. I did that because I want to draw some diagrams here. I want to, on this time axis, I want to show you the customers that arrive, the C sub n's. I want to show you the service time of customer Cn and the inter-arrival time. So let's start at time 0. Suppose the system is idle. And suppose want to get this lined up with a grid, so again, I'm going to have to play a bit of a game here. Just to move it over a bit. Okay. Suppose C1 comes at this point in time, call that C1. And the time when he arrives is, say, at 2 seconds. If you can see the grid, it's 2 grid marks over. And suppose the service time that customer comes in with is 3 seconds. Now, how much unfinished work is there instantly after that customer arrives? Yes? 3, exactly. So let's draw that. Suddenly, this unfinished work jumps up by 3. And let me indicate that here. Now, until the next customer arrives, how will the unfinished work behave? Well, work is going to get done at what rate? How many seconds of work per second? Single server? 1 second per second, which means, as you might expect, this is going to drop down a rate at a slope -1. And then I'm going to let the next customer come in. So the next customer comes in right here, and that's at time 4. But let's assume his service time, this is C2. Let's assume the service time that that customer comes in is 4 seconds. Now, how much was the unfinished work just before that customer came in? 1. After he or she comes in, how much is it? 5. So we can all do arithmetic, right? So let's mark that down. Down to here. Yeah. And that's 5 seconds. Let's let another customer come in. Oh, by the way, can I now say what T sub 2 is? What's the interarrival time between C2 and C1? It's 2 seconds, right? That's between C2 and C1 arriving. Now, this is going to begin to drop down. I'm going to let it drop down for 2 seconds because at this next time, C3 is going to arrive 2 seconds after the C2 did. So let's put C3 right there. And let's assume that customer comes in with 2 seconds of service. So what's going to happen to the unfinished work? It's going to jump up by 2. It starts off at 3, jumps up by 2, so it ends up at 5 again. And let's assume the next customer comes in, C4, 4 seconds later. 1, 2, 3, 4. It's going to come right in here. That means that this is going to drop down. To here, down to 1 second. So we see this is C4. Let's assume this customer comes in with 2 seconds of service. And by the way, what was the interarrival time between C3 and C2? It was 2 seconds again. Between C4 and C3, four seconds. And he comes in with 2 seconds of service, so it's going to jump up now to a value of 3. And then we're going to let it die out. No customers come in before the system empties. And right there. And what time does that occur at? Well, if you make the simple calculation, that's at time 13. Because it's easy to see that the first customer came in at time 2, and how much was the total amount of service that came in with all these customers? It's a sum of all of that, right? It's 7 plus 4 is 11. So 11 seconds of work plus 2 seconds of the arrival time. This time 13 makes sense. What I'm saying, basically, and it's pretty obvious, is that this interval is equal to the summation of all the service times in that interval. And it's also what we're going to call a busy period. Oops. That's the interval during which the server was continuously busy. Started out idle, ended up idle. Let's do the next customer, say 6. C5 comes in out here somewhere. That means that this interval is a period in which the system is continuously idle. So we're going to call this an idle period. And let's assume he came in with some amount of work. We don't have to say exactly what it is. And it takes off again. Now, later on, we're going to be interested in the busy period distribution and the idle period distribution because it's of some interest and it's actually a very interesting thing to look at. But we're not going to focus on that for a while. I just want to introduce that to you. Mainly, I want you to look at this picture, which is so valuable for you to understand. Oops. Similar to this picture up here, you can draw this picture as well. Now, I didn't choose the same number, so it's a little different. But both these pictures tell you what's happening in a very graphic way in this system. And I want you to understand it and feel comfortable with it, because from pictures like this is how you're going to be able to write down the equations driving the system, for which we're going to try to find solutions like the waiting time. Okay, so we can put a pause on that. We're not going to take this any further right now. Next thing I want to do is talk about the following. We talked about N of t. And if we take the limit of that as time goes to infinity, if the system is stable, then that limit should have some value. We're going to call it n bar, which will be the average number in system. The number in system, n of t, is at every point in time. Eventually, it'll settle down to some average value. And let's look at how many arrivals, what an arrival does. When an arrival comes in, what does that person see? It's Hello? Sounds like I'm talking. Okay. So I'm saying this result is a major result. It's probably the most famous. Speakers on? I don't hear them on. Hello, testing? Take this job that way. Hello?
We got that.
Hello? Hello? What is the problem here?
Okay, now it's on.
Testing? Testing? Yeah. It's hard to hear up here. Okay.
Okay, if that fails, you can turn this. This is off, but you can turn it on. Sorry.
Okay. Now, if you recall, maybe I need to swallow this thing. If you recall, we earlier talked on one of the first days was that the rate of input to the system should be less than the capacity of the system to do work. In this case, so R over C should be less than 1, but R over C is just rho. That's the fraction of time the server is busy. And this is called the utilization factor. In queuing theory, the fraction of time the server is busy. Now, if you look at a long time tau, the number of arrivals in tau seconds is approximately lambda tau. And I'm going to let p sub 0 be the probability the server is idle at some arbitrary time in that interval. In, say, 0 tau, the interval 0 tau. That implies that the server is busy tau minus tau p0 at the time. Now, the number of customers served in this interval, 0 tau, is equal to the amount of time the server is busy, which is tau times 1 minus p0, divided by the amount of service each customer needs, which is x bar. So how long you're busy? Tau 1 minus p0 seconds. How much service for each customer? X bar, the ratio, is the number of customers served. So the number of arrivals in that interval is approximately equal to the number served in that interval. So it says that lambda tau, the number that arrived, is equal to the number served, which is tau 1 minus p0 over x bar. As tau goes to infinity, we basically show that lambda x bar is equal to 1 minus p0, which is rho. So again, that's a fraction of the time the server is busy. It's a quantity that's going to occur over and over again. Okay, now all this was hand-waving, if you will, a bit. I want to now launch into a more detailed discussion. It's all about stochastic processes of interest. I'm going to take you through some definitions and some relationships that are of value to you well beyond your study of queuing theory. We're going to use some of it as well, but I'm going deeper than you really need to give you the bigger picture, okay? So we have a stochastic process, x of t. And it has three parameters, as we know. First of all, there is the state space. Namely, the values it takes on, possible values of x of t. Now, if the possible values are finite or countable, if you will, then we say we have a discrete state process. If they're continuous over some interval, then we have a continuous state process. That's all about the state space. Now, the second thing is the index or time parameter. Again, there's two cases. It could be finite or countable, just like before for the state space. Does it appear on the integers? Then it's called a discrete time parameter. Again, all these are obvious. And sometimes it's called a stochastic sequence. Or, basically, the time parameter can be anywhere in an interval. Just like the state space. And of course, that's going to be called a continuous time parameter. In the case of the finite case, we usually denote it as x sub n, where n is the discrete time. And we call that a stochastic sequence. In the case of continuous time, we call it x of t, as I started out, and that's basically called a stochastic process. Now, the third thing, besides the space and the time parameter, is basically the statistical dependencies. Among the x of t or the x of n. You got a bunch of these. How are they related to each other? So basically what we need is a joint distribution at all times, be it discrete or continuous. So I'm going to introduce a little bit of notation now. I'm going to write x with a bar below it to indicate a vector. And that's going to be this vector of x of t's, namely x at time t1, x at time t2, all the way out to, say, x at time tn. And I'll often use an underbar to represent a vector. We're not going to spend too much time on it, but you see it occasionally. So what do I need in order to describe these statistical dependencies? I need the following. F sub capital X, and I could have put a vector below it if you like, but generally I don't need to, but it's expected, of a set of numbers x and t. And that's defined as the following. The probability that x of t1 is less than or equal to x1, and x of t2 is less than or equal to t2, less than or equal to x2, dot, 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 out to x of tn, less than or equal to xn. And this has to be given for all values of the vector x, which I wrote a moment ago, x of t1, comma, dot, 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 x of tn. And for all time, which if I write that as a vector, is the t1 t2 out to tn, and for all n. Now, how do you like that kettle of fish? That's an almost impossible task. So let's make that note. This is a huge task in general to give all that description. Happily, there are many interesting cases that we're going to describe. A bunch of special cases, which I'm going to take you through in a moment. So let's say there exist many interesting cases. Namely, interesting stochastic processes. Which permit a simpler description. So I'm going to take you through a few of those. Because this thing up on top is really a huge task, and one that's very difficult to do in general. So in some sense, we're going to limit ourselves to the things we can handle. But they're very interesting cases. Okay. So case A. Something you've seen before, something called a stationary process. It has the following property, that capital F we're after, capital X of x semicolon t plus tau is equal to f sub x of x and t. Namely, a shift in time doesn't affect the relationship among these variables. And there's a whole study of stationary processes. There's something called wide sense stationarity. If the first and second moments are independent of tau. Not the whole distribution, as said above, just the first and second moments. Independent of tau. Now, clearly, stationarity implies wide sense stationary, but not the other way around. So wide sense stationary is not as restrictive. People use wide sense stationary processes in the theory of communications quite a bit, because a lot of it is second order theory, and this talks about the second order capability. Okay, that's a stationary process. Next, I want to talk about independent processes. And instead of using the cumulative distribution, capital F, I'm going to use the density, little f. It's a little easier to write down. So I'm going to say for independent processes, the density on that vector x of x and t is defined to be, and what I mean by that, remember that big X is a vector, it's f sub x1 through xn of x1, x2 through xn, semicolon, t1, t2 through tn. That's what I mean by the shorthand f of x. And the independent process definition is that that is equal to, what do you think? The joint density of n of these is the product of each. Powerful. Really simplifies things a lot, and it gives us considerable flexibility. We're going to use those a lot. So let's write that down. That's f sub x1 of little x1, semicolon, t1 times f sub x2 of little x2, semicolon, t2, etc., f sub xn of little xn, semicolon, tn. We've seen this over and over again before, but it gives us an enormous amount of flexibility, and it's not an uncommon case, and those are the kind we're going to consider. Namely, we're taking independent random variables, basically, in this process. Now, it turns out if it's a continuous, if it takes place in continuous time, that turns out to be white noise. Okay? Continuous random process will become out white noise. Now next, and a very important case, is something called a Markov process. Now who is this Markov? It's A.A. Markov. Brilliant person. I'll show you his picture at one point. Out of his results came Markov chains, Markov processes, of great value in the study of queuing theory. In 1913, he found this idea of a Markov process by taking, he's Russian, taking the Russian Pushkin, the poet, and finding in his poem Eugeny Onegin, a very famous poem that Pushkin wrote, and he asked, how often does a vowel follow a consonant? How often does a consonant follow a consonant? All the four cases. And he has sort of a four-state system, and he wanted to find those probabilities. Begins to make you think of what we now recognize as a Markov process. But it came out of this very simple study of his. And it was a classic paper. He won a prize for this paper, by the way. So there's a richness behind this idea. So let's define what it is. Okay. A Markov process, which I'll abbreviate by MP, with discrete state space is called a Markov chain. We're going to use lots of those. A set of random variables, xn, forms a Markov chain. I'll use MC for Markov chain. If the probability that the next state or next value, if you will, is xn, the probability that it is equal to xn plus 1 depends only on the current state xn. That's for a Markov chain. Now that's a very powerful statement. By the way, if you think of a simpler system, it could be that the probability that the next state is xn doesn't depend upon any previous state. Toss a coin. This says the coin is going to depend upon where you started from. You can create something beyond Markov processes. Suppose the current state's value depends upon the last two states. That's a deeper kind of Markov chain. This is a particular symbol. It's not as trivial as nothing depends upon anything, but here's a very simple dependence. What happens next depends only upon where you are right now, or what's happened right now at the last time. Okay, so I'm trying to give you a bigger picture of how these things fit in. So in other words, what I'm saying is that the full past is summarized in the current state. Everything about the past, as it affects the future, is summarized in the current state you're in, the current value. Now for a continuous time, I just did a discrete time, for a continuous time, Markov chain, but I'm going to call it a Markov process now because it's continuous time. Since the current state is totally summarizes the entire past, that's all you need to know about the past, just like in the chain. And we're not free to specify how long the process has been in its current state. mean, think about that. If the value of the current state is all I need to predict the future, then knowing how long I've been in that current state is extra information, which by definition I don't need. In order to predict the future as well as anything else, I just need to know what state you're in, which means I should not be allowed to specify, I should not need to specify how long you've been there. Okay? Well, this implies, as it turns out, we're going to see later, that therefore the time and state has no memory, and it turns out the distribution for time and state in that case is exponentially distributed. We're going to prove that later. Yes? You mean you can't read my handwriting? By the way, the book very clearly lays this out. So you don't have to copy very careful note to read, but I'll read it to you. For continuous time Markov process, since the current state totally summarizes the entire past, then we are not free to specify how long it's been in its current state. I shouldn't have to. There's nothing about that can help me. It turns out there is a distribution of time in state which doesn't depend how long the state has been. And the reason that is, if I told you how long it's been, it doesn't affect how long it's going to stay there. For example, if you were waiting for a bus, and on average, buses come along every 10 minutes, and you've been waiting for 9 minutes. I told you, you've been waiting 9 minutes. Well, you're sort of biased the bus is pretty soon to come. Okay? That information could bias what's going to happen in the future. There are some cases where it doesn't, the exponential. But the exponential says no. Knowing what's going to, how long you've been there, the rest of the distribution looks as if you've just started out. And we'll go into that in detail later. I'm just warning you, the exponential distribution comes out. And for discrete time, that turns out to be a geometric distribution instead of an exponential distribution. Continuous time, this implies an exponential distribution for time and state. Discrete time implies a geometric distribution. Okay. So the Markov property is written as follows. It says the probability that x of Tn plus 1, taken on the value little xn plus 1, given a whole bunch of information that at time Tn, you instate xn, and at time Tn minus 1, you instate xn minus 1, dot, 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 all the way out to time 1. The Markov property says that that probability is no surprise. It's equal to the probability of the same thing of x of t n plus 1 is equal to xn plus 1, given only the most recent information that x at time tn is some number, say xn. That those two probabilities are the same, which means none of the rest of this mattered. Only the most recent one. It turns out that Markov processes are central to queuing theory, and we're going to focus on them. We'll expand them some more. But meanwhile, I want to go a little further. Next I want to do, you have to turn it off. Oh, you did turn it off. Yeah. Good. Take a break. I put it a little closer for you.
Yeah, thank you.
Thank you. What's going on with this?
I have no idea. I like.
I'm going
unsealed
to turn
the,
this off for the minute.
Yeah.
Okay, let's get going. So I want to continue beyond the Markov processes. As I say, they're very important. The next thing I want to discuss is something called birth-death processes. Now, some of you are familiar with all of what I'm talking about here. Some are not, so I'm going to go through a bit of detail here. First of all, a birth-death process is a special case of a Markov process. The defining condition is that you move among nearest neighbors only. Namely, if x sub n is, say, the discrete value I, then xn plus 1 must be I plus 1 or I minus 1. And the model is pretty clear. If you think of what birth-death means, you have a population. If there's a birth, the population grows by 1. If there's a death, the population drops by 1. It's a rather interesting model. It comes up in queuing theory quite a bit. Now, before we go much further, I'm going to pull up a diagram from the book. That's on page 25, as you can see. And what we just talked about, essentially, was a Markov process. And we talked about a birth-death process. Again, what's true for the Markov process is that the time and state is memoryless, but the way you jump between states is arbitrary. It could be any set of numbers. The birth-death process says, yes, it's a special case of a Markov process. It's memoryless, but the PIJs are specific. They must go, J must be I plus 1 or I minus 1. It's a special case. And we're going to dive into all these processes, but for a moment, I want to move up to something called a semi-Markov process. So let me introduce that as the next topic. This is case E. It's a semi-Markov process, which, as you see in the diagram, are denoted as SMP. And first, we're going to look at discrete time. Discrete time semi-Markov process, SMP. Now, the thing that characterizes a semi-Markov process is that the f tau does not have to be memoryless. It can be arbitrary, okay? Arbitrary distribution of time and state. But what's interesting is, I'm going to make an asterisk here. At the instant of state transitions, when you move from one state to another, it behaves as a Markov process. So when it moves, it behaves like a Markov process at those instants. Now, what do I mean by that? In the case of a general semi-Markov process, if I tell you what state you're in, that helps predict the future. If I tell you how long you've been in that state, that may also help you. It's not memoryless necessarily. But when you jump from one state to another, how long have you been in that new state at the instant you jump? Yes, tell me. 0. You just jumped in, so that you know how long you've been there. It's 0 seconds. At those instants, the only thing that affects the future is the state you're in. So it has a kind of Markov property. And in fact, we're going to call that, we're going to say at those instants, we have something called an embedded Markov process. Or in this case, if discrete, it's Markov chain. Which means that we've embedded into the time axis certain points when this baby looks like a pure Markov process, but not at other times. Once it's been there for a while, then you really have to know how long it's been there because there's memory in that, how long you've been there. But at these instants, when it jumps, you don't care. It's 0. You know the answer. It's 0. And you know the distribution of time to finish. So we're going to use this very nicely when we get to some of the queuing systems. So it's embedded Markov process or Markov chain depending upon the state. So that's what this thing is. And so for everything else we talked about falls under that. But now I want to go someplace else. I want to do something called a random walk. And again, for this case, the time in state will be arbitrary. But in fact, you're going to move specifically, Pij will be kind of related to the difference between j and I. Okay, so it's a little special case. But because it's not memoryless, it's still under the semi-Markov process case. So let's here talk about random walks. And those of you who did or should have studied probability theory have seen these things. Random walks, you walk among different states, and how long are you there? When's the first time you get to a particular state? Questions like that come up. So let's talk about that. A particle is moving among states. In some, say, discrete state space. For example, we could say discrete. We don't have to, but let's do it now. And what we want to know, we're interested in the location . The location of the particle in that space. So let's look at a sequence. We're going to call it S sub n, capital S sub n. And say it's a random walk if that sequence Sn is equal to x1 plus x2 plus dot 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 plus x sub n for n equals 1, 2, etc. Namely, it's moving in such a way that you're adding together the points it's been in before. You're adding up a number, basically. And we'll set S0 equal to 0, just to get it started. And what is xi? This set of numbers xi is a sequence of independent random variables with a common distribution. In other words, they're IID, independent, identically distributed random variables. Now, if the instants are discrete, then we say we have a discrete time random walk. And obviously, if it's continuous, we get a continuous time random walk. The intervals between jumps, if you will, between steps, is arbitrary. Between transitions. By that I mean the distribution of time. Hence, it's a semi-Markov process. And we'll have occasional to see this thing come up. Again, if you look at my picture here, there it is. And basically, each step you add to the previous step. Okay. Next one we'll talk about is the renewal process, which is similar. It's also known as a recurrent process. I warn you, there's a lot of definitions here. We're almost done, by the way. This is related to a random walk. It's similar. But the focus is on counting the number of transitions. And again, when you want to do it as a function of time. Again, distribution between transitions is a common distribution, that f of t we talked about. And again, to get you started, we start at 0. That is, x of 0 is 0. The first step gives you a count of 1, count of 2, etc., with the time between counts being arbitrary. And coming back to our picture, that's this fellow right here. And notice both the random walk and the renewal process could have exponential times between their jumps and their steps. So it falls into the Markov process as well. And in fact, if you notice, there's a couple of processes here, a Poisson process and a pure birth process we're going to see later, both of which are special cases of random walks and random renewal processes. So the picture I'm giving you there is more than you really need. I just want to let you understand where we are as we dive in deeper. We're going to dive deep into a pure birth process pretty soon and a Poisson process. But I want you to understand how they fit into the general scheme of things. That's the whole point of this. Okay. Having said all that, I finally want to now get to something called a discrete time Markov chain. And in some cases, some classes, this is where queuing theory begins. They start right here. Instead of the bigger picture, they go right with a discrete time Markov chain and play around with it. So you can almost do a reset. Don't do it, but you can forget everything I taught you about and begin here. It should be, in some sense, self-contained. But I want you always, this is, for your good, to have the big picture, be aware where you are in all of this. It's not some funny little thing that happened to be interesting. It's a piece of a bigger picture. Okay. So we have discrete positions in discrete time. And I'm going to use an example. It's in the book as well. I'm going to use the example of a hitchhiker. So some hitchhikers hitching around a bunch of cities. And whatever city he arrives at today, at midnight, the first automobile that comes around that gives him a ride, he'll take. And he'll take him to some other city. He'll stay in that city until midnight comes. He'll take the first ride that comes around again. So he doesn't know where he's going to end up. He goes hop, hop, hop. Discrete time, every day, one change. Okay? He may actually come to the same city he was in. So I want to do an example. I'm going to show you some cities, okay? We're going to number the cities and give them names. So this will be the first city. I'm going to give it an arbitrary name. I'm going to call it Abra, as in abracadabra, if you've heard of that. And there's another city here. I want to make it as pretty as I can. City 1, and we're going to give its name Zeus, just because I'm being cute. Okay, it's an arbitrary name. And sure enough, there's a city 2, and I'm going to give it a strange name. I'm going to call it Sukhsamad. Anybody figure out what I'm doing with these names? Damascus, Sukhsamad is Damascus backwards. And Zeus is Suez backwards. And Abra is Abra. Okay. Just playing around. You see there's some other cities I have in my book which are more fun. Okay, now. Remember, the hippie will accept the first ride after midnight. So let's assume he's in the city of Abra, and a ride comes along. Let's assume there's only 2 places he can go. he can go from Abba to Zeus, Abba to Suksamad. And let's assume the probability of that, we're going to give it some probabilities. 3/4 of the time, he's going to get a ride to Zeus. And 1/4 of the time, he's going to get a ride to Suksamad. Now, when he gets to Zeus, next day, he starts hitchhiking. He can go back to Abra. He may not like it, but that's what happens. Or he can go to number 2, Suksamad. And let's assume the probabilities there are 1/4 to go back to Abra, and 3/4 to go to number 2, Suksamad. Now, when he gets to Suksamad, things are going to happen. He could end up with a ride going to Abra. He could end up with a ride going back to Zeus. Or he can get stuck with some guy who goes out of town and comes right back in. And let's put some numbers on that. To go from 2 to 0, we'll say is probability 1/4. From 2 to 1 is going to be probability 1/4. And half the time, he ends up back in 2 again. So this is an example of a discrete time Markov chain. The amount of time he spends could be geometric, as you will. It comes out of this. So let's put down some comments. The position of the hippie at some time in the future is a random variable. You don't know where it's going to be. And of course, we want to find out where he's going to be with some probability. Okay? So let's identify the cities. Let x sub n denote the city the hippie is in on day n. Jumping around, okay? Now I'm going to define something. I'm going to define the sequence of random variables x1, comma, x2, comma, etc. Define it. It forms a discrete time Markov chain if, and we know what the definition is basically, if for all n equals 1, 2, etc., and all possible values of the random variable we have what we expect. I defined it before. The probability that the city at time n is some city named x, that xn takes on some value x, given that the city at time 0 was x0, and the city at time 1 was x1, dot, 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 down to city at time xn is xn. Well, we know what that has to be. It's got to be only dependent on the last one, which must be equal to the probability that xn equals x, given only that xn equals xn. Namely, the probability of being in state n next, oops, That should be an n plus 1, I'm sorry. N plus 1 here, and n plus 1 here. That next city, n plus 1, knowing the entire past, only depends upon where you are in the current city. I'll write it out again just to emphasize it. The entire past is summarized by knowing the current state. And that is all the future depends upon. Now, if you look at the picture, if you know you were in city 2 for the 10 most recent days, that doesn't affect what's going to happen in the future. If it was there for 10 days, 2 days, 1 day, 5 days, it doesn't affect what's going to happen in the future because you're going to toss an independent coin, if you will, each time. So the history doesn't matter except the current state. And this example makes it pretty clear. Okay. Now, when are you in city I at time n? We say the system is in state I at step n. And by instead of staying state I, I'm going to call it E sub I. When I write down E sub I, I mean the state I at step n. So when I say we're in state EI at step n, I mean you're in city I at time n. Now we got to get started, okay? So to get started on step, if you will, day 0, we use an initial state probability. Initial state means the state at time 0. Namely, the probability that x at time 0 is equal to I. You could be in any state initially, and I'll give you that distribution. Now I want to go back to this equation on the top of the screen, and I want to give it a number because I'm going to refer to it later. So let's call this equation 1. And I want to point out that equation 1 is known as a one-step transition probability. And by the way, I'm using this example, but I'm creating some general statements here. This, these comments, this probability equation 1, doesn't depend on the example. The example just helps you think about what I'm discussing. Now, if the transition probabilities are independent of time n, And I want to focus on the word, I want to add the word time here, not just put down n, to remind you that's a time index. Time n. Then we have something called a homogeneous Markov chain. And we denote in that case, notice up here on equation 1, the index n seem to matter. For example, equate this p of xn given equals x given xn equals xn. That could depend upon the index n. 20 years from now, that transition probably may be very different. If it's homogeneous, it doesn't change with n. And then we're going to use a simpler notation. Then we denote p sub ij as the probability that xn equals j given xn minus 1 equals I. Now I went from n plus 1 to n, it doesn't matter. These are now the transition probabilities. On the left-hand side, there's no notion of n. Just from one step to the next, you're going from I to j. Now, we're going to talk only about homogeneous Markov chains for most of the time from now on. If we don't, I'll warn you. But right now, it's homogeneous, which means the transition probabilities do not depend upon time. Okay? Now, I'm going to give you a bunch of definitions. Please bear with me. It's a little ugly, but don't get lost and don't ignore these definitions, because I'm going to be using these phrases as we go on. You know, it's just like in linear algebra. If you lose what they mean by a field or a group or a ring, you're lost. Okay? So let's be aware of what these names are. They're not just dull, if you will. Okay. I want to talk about something called the m-step transition probabilities. And they're defined as p sub ij with a super m. And that's the probability that xn plus m is equal to some state j, given that at time n it was at I. So just wondering, in m steps, if you started at I, will you end up in j? You could bounce all over the place. And there's a recursive formula for this. That we'll occasionally use. And it looks like the following. That p ij m steps is the sum over all values k for pik for m minus 1 steps. Namely, you're going to go from state I to state k in one fewer steps, and then, of course, from k to j in the last step. And that's for m equals 2, 3, etc. So it just says it's a way to find these Pij super m's, but it's an obvious definition, and occasionally we'll use it. And by the way, you're going to find things like this in your, not this equation, but the idea of going one step to the end. I'm going to ask you to find sums of certain types, and you have to express it in terms of sums close to that. Okay, next definition. This is an important one. A Markov chain, they're all important. A Markov chain is irreducible and that's the thing I'm trying to define, irreducible. If every state can be reached from every other state, now, the use of the word irreducible has meaning. And as example, I go back to our example. Is this Markov chain irreducible? She says yes, and she's right. You can get from every state to every other state. If, however, this is value 1, which means this is gone and this is gone, that means once you get to state 2, you're stuck there. So you can't get from state 2 to state 1, ever. This is gone. And so is this. That would not be, that would be reducible, if you will. So we want to consider irreducible. They seem to be the good ones where you can bounce everywhere. You're not isolated from any place. So another way to say this is, that is, for every pair of states, in the example, what is a state? A state is a city. I don't mean to play with those words. Okay, but the city you're in is the state you're in. For every pair of states, and let's call those two states EI and EJ, for example. That's a pair. There exists a number M0, which may depend upon I and J, such that P sub ij of M0 is greater than 0, which means you can get from I to j with some number of steps. Okay, more definitions now. And again, I remind you, this is all in the book. You can read it slowly there with better handwriting. Okay. Let A be the set of all states in the Markov chain. Then a subset let's call it A sub L, is closed. I'm defining closed now. If no one-step transition is possible, from any state in that group and from any state in AL, to any state in the complement of AL, and I'm going to write that as A sub L super C for complement. That means you're stuck within your own group. You can't get out. If A sub L is only a single state, and let's say that's state EI. Then it's an absorbing state. I've just defined what I mean by absorbing now. And it turns out there were necessary and sufficient condition for state EI to be an absorbing state. Is no surprise that PII equals 1. Once you're there, you stay there. So it's sort of a trap, like that state 2 I showed you before. Okay. So continue with some of these definitions now. If A is closed, oops, and does not contain any proper subset, which is closed, then we have an irreducible Markov chain. Otherwise, the chain is reducible. If a closed subset of a reducible Markov chain contains no closed subsets of itself, then we have an irreducible sub-Markov chain. So just define that. Okay, now going a little further. Again, I'm just throwing definitions out at you. We're going to be using these terms as we go along. I want to define the following quantity. Quantity called f sub j of n is the probability that the first return to EJ occurs n steps after leaving EJ. So you're in a particular state, you leave it, bang, 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 you hop around. Sometime in the future, when you come back to that state, you basically hit the first return to that state. Now, if you hit it again, that's no longer a first return. You hit the first return already. Okay? The probability of ever returning to EJ is the following. I'm going to denote that by f sub j without a superscript. That's clearly the sum over all possible returns, first returns, from 1 to infinity of f sub j super n. There's no repeats here. The first return could happen on step 1, step 2, step 3, etc. If ever getting there, the sum of all of them. Now, I want to classify the states of a Markov chain according to this Fj, the probability of ever returning. So here's a few cases. If Fj equals 1, then we say we have a recurrent state, EI. On the other hand, if Fj is less than 1, we have a transient state, EI. If the only steps at which the Hipparcos will return to EJ are a multiple of some number gamma, then it's periodic. I want to write that out now. If the only steps at which, I'll use the word Hippie here as just to remind you, can return to E sub I are steps gamma, 2 gamma, 3 gamma, etc., where gamma is bigger than 1. And is the largest integer. The largest such integer, if you will. Then EJ is said to be periodic with period gamma. Now it's pretty clear. If gamma equals 1, then in fact EJ is aperiodic. I want to write a little bit more to complete this little section. Now let's consider some recurrent states. Let's consider recurrent states. What does that mean? Fj equals 1. you're going to return eventually. Then the mean recurrence time, on average how long it'll take to come back, and I'm defining that quantity now in words and then in symbols, of Ej, of course, is defined as capital M sub j. And what's the mean of a variable? It's the sum of all possible values from 1, say, to infinity of the thing I'm forming the average, namely n f sub j super n. Let's call this equation 2. In other words, it's the average time to return the state Ej. Now, I'm almost done. If m equals infinity, then it's still recurrent, but it's a lousy recurrence. On average, it takes you an infinite time to get there. So we say, then Ej is recurrent null. If mj, I'm sorry, there was a j here, I left that out, state j. If mj is less than infinity, then Ej is recurrent non-null. Now, these recurrent non-null states, in some sense, are the states we like. You can get there, in average, a finite amount of time, and you bounce around among them. So in some sense, we're going to consider those the good states. Recurrent null takes an infinite time to get there. That's not too interesting. So finally, I want to define quantity pi sub j super n as the probability you find the system in Ej at time n. In other words, pi sub j super n is the probability that xn equals j. Now, given all these cumbersome definitions, there are two key theorems we're going to take up next time, which tell you all you need to know about Markov processes, the Markov chains. But it's in terms of some of these definitions. Okay, I know it's boring to get definitions thrown at you, and they'll get more familiar to you as you go along. But the theorems are all about this. So let's meet on Wednesday. You've got the next homework assignment in your pants. You can get started on them. Okay, any other questions? Yes? Yes, it could. Nobody said it doesn't. It does definitely depend upon you. The question is, doesn't pi j of n depend upon initial state? Yes, it does. And I haven't implied otherwise from here. And it will, certainly. For example, pi sub j of super 0 is the initial state at state 0. Right? So, of course. Anything else?